So the definite integral as a limit of Riemann sums. So let f be a function defined on a closed interval ab for any partition p of ab. Let the number c be chosen arbitrarily in the subinterval between x, k plus 1, xk. If there exists a number I such that the limit of right Riemann sums as n approaches infinity, no matter how p's and c's are chosen, then f is integrable on AB, and I is the definite integral of f over AB. Right? So it doesn't matter how we partition. If the limit of right Riemann sums exists and we get a value, that value is the value of the definite integral. So we can find the definite integral by taking the limit of the right Riemann sums as n approaches infinity. We also have another way to find the definite integral. Let f be a continuous function on AB. If f is any antiderivative, so that's a capital F, is any antiderivative of f, and that's a lowercase f, defined on AB, so it has to be defined on the interval, then the definite integral of f from a to b is defined by, so this is read as the integral from a to b of f of x dx. The f of x, that's the integrand, and it is the derivative. We integrate, and that gives us the definite integral. It is the antiderivative, which is essentially the original function missing a constant, perhaps missing a constant, because we know when we take the derivative we lose the constant, so the constant's been lost. Right, so the definite integral is also the same as the limit of the Riemann sums and the area under the curve. Right, so now we have a second way, and that is to find the antiderivative and evaluate. So there's the limit of the limit of Riemann sums. We have the finding the antiderivative and evaluating, integrating and evaluating, and now we have a third way, and we're going to talk about that in just a second. Actually, let's go to the third way, and then I'll come back to the notation. And then the third way would be the geometric interpretation of the definite integral, and that's the definite integral as area. And if we know if we have some positive and negative parts, then if it's all positive, then the definite integral is an area. If it's all negative, it's an area, but it's below the x-axis, making it negative. But if we have some negative and some positive, it ends up being a net change in area, because the positive and negatives will cancel each other out, and just whatever's left over, the net change will be what we're left with for the definite integral. There are some functions where we'll need to evaluate some integrals definite integrals where we'll need to evaluate as we need to use the geometric interpretation and evaluate as an area. So for instance, the integral of f minus x squared on negative 2 dx, to calculate this integral we would need to find the area under a semicircle, because we'd be darn stuck finding it any other way. All right, so let's just talk about the notation for a second. All right, so in the notation, the f of x is called the integrand. It's also the derivative that we're going to take the antiderivative for, and then evaluate if we're finding the definite integral. And in this lesson, we're looking at the definite integral. A and b are the limits of integration. A is the lower limit, and b is the upper limit. And regardless, even if a were larger than b, A is the lower limit and B is the upper limit. It's their location that makes them the lower and the upper. For now, the symbol dx has no meaning by itself. It's all one symbol. It simply indicates that the independent variable is x. And you can also think of it as the f of x's as being heights of rectangles, and the dx as being a width of a rectangle. And as the width goes to 0, the number of partitions is going to infinity, because the definite integral and the limit of the right Riemann sum is the exact, as n goes to infinity, is the exact same value. And we'll show that. So the definite integral, the procedure of calculating an integral is called integration. The definite integral of f of x dx on AB is a number. It does not depend on x, right? But it does, the they do have to match. So if x is the variable, then dx needs to be the integration, the value of integration there. So if we need to have a dt if t is the variable, and we need to have a dr if r is the variable. Those two need to match each other. And we did that one. All right, so we are going to, so sometimes we can find it as an actual area because it's a nice geometric shape. And sometimes, or it can be broken into geometric shapes, and sometimes it cannot. Sometimes we can use the limit of Riemann sums because we have a power rule for sigma we have a power sum for sigma we can use, and sometimes we don't. And sometimes we can integrate by finding the antiderivative and evaluating, and sometimes we don't have a way to find the antiderivative. Right? So you'll find that we won't be able to integrate every single function that there possibly is, but you'll be able to integrate all the ones you'll run across in this class in some fashion. All right, so here's our first one. We have 4x minus x squared dx evaluated on 0, 4. And we're going to do this as a limit of Riemann sums, and then we're going to use the new rule that we have now learned, finding the antiderivative, integrating, and evaluating. All right, so let's do this one first of all as a limit of Riemann sums. Change in x is 4 minus 0 divided by n, or 4 over n. Our next step is to find x. Right? And this is the x for the right Riemann sum. So we start off with 0, and then we add a change in x. Right? So that's therefore just 4nj. We plug that back into the function. So we substitute x into the function, and simplify. So we have 4 times 4nj minus 4 over nj. For some reason I keep saying 4n, but it's 4 over n, but you see that. 4 over nj, and that's all squared. All right, so this would give us 16 over n times j minus 16 over n squared times j squared. And then we're going to do the limit of right Riemann sums. As n goes to infinity. So it's a right Riemann sum with n partitions where n is going to infinity. And that would be our change in x, which is 4 over n times sigma. And that would be j equals 1 because it's a right Riemann sum. So we start after the first value, the first change in x to n. And our function now is 16 over nj minus 16 over n squared j squared. All right, so now we'll split that up. So we'll split the Riemann sums. So we have r of n equals 4 over n, sigma j equals 1n, 16 over nj minus 4 over n, sigma j equals 1n, and 16 over n squared j squared. All right, so now let's factor out coefficients. So we have 64, r subscript n, 64 over n squared sigma j equals 1 to n of j minus 64. We'll have to remember to distribute that negative sign. 64 over n cubed, and then we have sigma, everybody's moved over, j equals 1 to n and j squared. So now we'll use the power sum, power sum rules for sigma. All right, so now that j, so this is 64 over n squared, and that j will now become n squared over 2 plus n over 2, and we'll distribute that. Then we have a minus 64n cubed times n, and the j squared becomes, using this the power sum rules, will become n cubed over 3 plus n squared over 2 plus n over 6. Right, so now we'll simplify. We distribute the 64 over n squared. The n squareds will cancel. 64 over 2 becomes 32. And then we distribute the 64 over n squared to the n over 2. That'll be 32 over n. We'll distribute the negatives now. Distribute the negative 64 over n cubed. The n cubes will cancel. And that's going to be minus 64 thirds. It does not reduce. And then minus the 64 over 2, and the 2 will cancel to a 32 in the numerator and an n in the denominator. And then minus, and well, 64 over 6 reduces to 32 over 3, and we'll be left with an n squared in the denominator. So now we're going to take the limit. As n goes to infinity, right, and that would be r subscript n, r of n, right, r with n partitions. The right Riemann sum with the infinite number of partitions is the limit as n goes to infinity of, let's combine the 32 and the 64 thirds. So 32 times 3 is going to be 96. 96 minus 64 is going to be 32 thirds, right? 96 minus 64, yeah. And then the 32 and the those will cancel each other out. And then we also have minus 32 over 3n squared. Right? And when we take the limit, that's as n goes to infinity, we have 32 thirds minus 0, which is 32 thirds. And there we go. There's the area under the curve as a right Riemann sum, with all your steps color-coded. I have to say, I think the color coding really makes a difference. Last year I had it all one color. It looks so much easier, I think, to follow with the color coding. Gives you all your steps. Let's do the same thing, but now let's integrate and evaluate. All right, and so 32 thirds is stuck. The area of the region there is stuck. But that should be the answer. What's the answer we got with when we took the limit of the Riemann sums? Better be the answer we get when we integrate and evaluate. So it's stuck on this picture. I think I had to cut and paste. I think I had my images disappear on me. All right, so I'm going to write our integral, just kind of move it away here. All right, so we're using the power rule, right? But this time we're going the other way. Right? We have power rule for derivatives where the exponent moves in front. If there's a coefficient, we multiply it, and then we decrease the exponent by 1. Well, now we're doing the opposite, right? So instead of multiplying, we're dividing. Instead of subtracting, we're adding. So this is going to be equal to, so we'll have 4x, and now this is to the first power, we would add 1, so now that would be a 2, and we would divide by that same thing, minus x, 2 plus 1, so that would be 3, and we would divide by 3, and we're going to be evaluating that from 0 to 4. All right, let's reduce. So that would be 2x squared minus x cubed divided by 3. Now we have two terms. You got to be careful with your order of operations. All right, so now I'm going to plug in the 4 everywhere, and then we're going to plug in the 0 and subtract. Of course, plugging in the 0 is quite easy on this one. But what if it were on a 0? What if it were a 1 or something like that? Right? Then we have to be careful with our order of operations. Right? So this would be 2 times 4 squared minus 4 cubed divided by 3. So notice I plug a 4 in everywhere. All right? And then I like to do this parentheses, all right? Because you simplify everything there for the 4. You simplify everything for the 0, and in this case it's a pretty easy simplifying, and then you subtract the results from plugging in the 0, the lower limit, from the results from plugging in the upper limit. All right? Now this one, of course, I've got 2 times 0 squared minus 0 cubed divided by 3. Well, that's 0. All right, so this would be 4 squared, 16 times 2 would be 32. Minus 64 thirds, and then we would simplify that, and then it would be minus, well, that's minus 0, so no big deal there. 32 is the same as 96 thirds minus 64 thirds, which is 32 thirds. And interestingly, I'm more likely to make a silly error with especially when there's a lot of terms and I have to make sure I'm distributing negatives, I'm more likely to make an error there than I am with the limit of the right Riemann sums. Not that I recommend that you always do the limit of right Riemann sums. You do that when you're asked. You do this when you evaluate when you're asked, but you understand the connection between the two. Two ways to do the same thing, right? Just like the definition of the derivative and the derivative rules, the derivative shortcuts, you're doing the same thing, right? You're finding the derivative either way. All right, so here's our first one, all right? On this particular lesson, I'll be doing most of these both ways, so you see that they're related, and plus you get a little bit more practice with the limit of the Riemann sums and get a little introduction to being able to find the antiderivative and evaluate as both ways that you can find the definite integral. Right? And this is only for the definite integral, meaning we have boundaries. All right, so definite integral is area. If f is a positive function defined between a, so a and b are lower, and a's are lower limit of integration, and b is the upper limit of integration. And then the definite integral of f of x dx on AB represents the area under the curve from A to B. Right? So the value we get is the same as the area under the curve. Right? And it does have, now when it doesn't have any context, there's not much we can do to interpret it, but if this were a velocity, so back here, if this were a velocity function, then that 32 thirds would represent the distance traveled, right? Because the velocity is the derivative of position. So when we evaluate a definite integral, and if it were velocity, what we get is change in position, right? If it were the rate of something being poured in. So instead, let's just say instead, let's say this function represents the rate at which liquid is being poured into some kind of container. Then the 32/3 would represent, and let's just say there was nothing to start with, because we'd have to add, if there was a starting value, we'd have to add that in too. But let's say the container is empty, and that 4x minus x squared represents a rate of how fast something is being poured into. So it's the derivative. When we find the definite integral, what we would be how much was in the container. So let's pretend that 4x minus x squared, let's pretend that that's the rate at which water is being poured into a container, then 32 in gallons. Then 32/3 gallons represents how much water is in the container. Right? They may ask you that, so if it has context, when we take the derivative and we integrate and evaluate, we get the net change in something. And we'll do some problems later on as one of the last things we do. All right? And if it's positive, you can think of it as an area. If it's negative, well, it's an area, sort of an area, but it's under. It's under the x-axis. So f is negative function. Then the area between the curve y equals f of x and the x-axis is going to be negative as well. So then we have negative area. And it just means it's under the x-axis. All right, so let's look at this one. So we're going to do this 2 different ways. Actually, no, 3 different ways. Let's do it 3 different ways. All right, we're going to find this as an area of a geometric shape. We're going to calculate this out as a limit of the Riemann sum. The right Riemann sum is n approaches infinity. And we're going to calculate using the definite integral and that shortcut we learned. Right? And by the way, in a later lesson, we're going to learn a little bit more about that shortcut. All right, so here is our function. It is the function f of x equals negative, for some reason the negative didn't show up, negative 1/2 x, I'm going to write it here too, f of x equals negative 1/2 x plus 6, all right? And we're evaluating that on from 2 to 6, all right? So we don't care about, here's the function, right? But we don't care about anything before 2, right? Because our limits of integration are from 2 to 6. Right? And here we have, and here of course is the x-axis. All right, so we can calculate this one out as an area. And this one is all positive. This one's all above the x-axis. Yep, all above the x-axis. All right, so the area here is trapezoid. We have one base that is that 5? I'll simplify. Plug 2 in, I'd get, yes, 5. Because I'd have 1/2, negative 1/2 times 2 would be a negative 1 plus 6 is 5. It's a little hard to see what that height is. And then we have the other height here, and that is 4. Yes. Wait, no, 3. Excuse me, 3. And if you weren't sure, negative 1/2 times 6 would be a negative 3. 6 minus 3 is 3. So there's our bases. The height is the distance between them, and that is 4. So the area, here is an area. We can calculate this out, and it will be the exact same using all 3 methods. Right? So I have 1, I have 2, and then method 3 I didn't write in here. We'll write it up here, I guess. 3 that we're going to use is going to be the limit of right Riemann sums as n goes to infinity. So the area as a geometric shape is 1/2 times 5 plus 3 times 4. Half of 4 is 2, and 2 plus 8, 2 times 8 would be 16. All right, so that's what we got as the area. Let's see if we get that same area all 3 ways. Oh, let me put a, yeah, I'll do that on this page, and then I'll do the limit next. So this is going to be the limit of Riemann sums. All right, so let's find, first step, let's find x, or excuse me, no, let's find change in x, excuse me. That would be 6 minus 2 divided by n, so that's 4 over n. Then let's find x. And we take our starting value, so that would be 2 plus, and then 4 over n times j. And then substitute x into the function there. And we'll simplify. So that would be negative 1/2 times 2 plus 4 over n times j plus 6. All right, so we'll distribute that. That would be negative 1 plus that. So negative 1/2 times 4 over n. That's going to be negative 2 over n j plus 6. Let's combine those like terms. So we have 5 plus negative 2n over j. All right, so now let's take our limit of Riemann sums here. So that's going to be 4 over n sigma. J equals 1 to n, 5, and since it's minus, I'm just going to put minus 2 over n j. And now let's split the sigma. So we have 4 over n, sigma, looking a little icky there in the writing, j equals 1 to n, 5, and then minus 4 over n, sigma, j equals 1 to n, 2 over nj. Let's factor out coefficients. All right, so no coefficients on the first one. 4 over n, sigma, j equals 1, n, 5, minus, that would be 8 over n squared, sigma, j equals 1 to n, j. Now let's use the power sum rules for sigma. So that would be 4 over n times 5n minus 8 over n squared times, so that j now becomes n squared over 2 plus n over 2. And now we'll distribute and simplify. So the n's will cancel. This will be 20 minus, and then the n squareds will cancel. 8 over 2 is 4. And then minus, the 8 over 2 will cancel to a 4 in the numerator and an n in the denominator. And then let's take the limit. So we have r of n is equal to the limit as n approaches infinity of 20 minus 4, that's 16, minus 4 over n. And of course, that's just 16 minus 0, which is 16. Same as we got as an area of a geometric shape. How about that? So there's 1, there's 2. Let's do 3. Oops, somehow it didn't get written down. All right, it was negative 1/2 x plus 6 from 2 to 6. Okay. All right, so this is a nice easy one because we can just undo the power rule, right? So this is going to be equal to, actually I'll put the equals here, -1/2 x, right? And that would be 1 plus 1, so that would be x squared, divided by the same thing, divided by 2, plus, I'm going to put parentheses here because it's two terms, plus 6, and then we increase, so now it has 6 times x to the 0 power, so 0 plus 1 would make that x to the first power, and if you divide by 1, it's still the same thing, right? So the antiderivative of 6 is 6x, because who has a derivative of 6? 6x does, that's who. And we're evaluating that from 2 to 6. Let's simplify that. So negative x squared divided by 4 plus 6x from 2 to 6. All right, now we plug in the 6 everywhere. So negative 6 squared over 4 plus 6 over 6. We find that, and then from that we're going to subtract what we get when we plug in the 2. Oh, and don't forget to write the square. And the negative is not squared, right? So the negative belongs there, because the negative is in front of that x squared. All right, so negative 2 squared over 4 plus 6 over 2. Wait, oh, how did that happen? How on earth did my 6x become a 6 over x? No explanation for that. It went for a walk. I guess I was putting the 4 underneath. I wanted to put the x underneath. That doesn't belong there. It was 6x. The antiderivative of 6 is 6x. I just said that. All right, now we have our x in the place where it belongs. Crazy. All right, so this would be negative 36 fourths plus 36 minus, all right, so this would be negative 4 over 4 plus 12. Then let's simplify in the parentheses, and then we can subtract the second from the first. So this would be a negative 9 plus 36 minus negative 1 plus 12. Negative 9 plus, I should keep putting equals here. Negative 9 plus 36 is going to be a positive 27. And then that's going to be minus 12 plus a negative 1 is 11. And 27 minus 11 is 16. There we go. 3 ways. So you should be able to connect the 3 ways. As an area, a geometric area, when we can actually calculate it out as a geometric area, as by integrating and evaluating, and the limit of Riemann sums. And I think this is, I'll finish off this one little part, and then, no, actually I'm going to stop here. I'm going to stop here. I'll do the next one on the next video. Thanks for watching. Bye for now.